All right. Okay, so on Wednesday, we talked a little about constructing basic non-parametric priors. We spent a lot of time talking about parametric distributions, specifically the Dirichlet distribution. And then we spent a bunch of time extending that to the infinite dimensional case. And that gave us the potential to create models where we don't have a fixed dimensionality, right? And that was useful for cases where we either don't know the appropriate dimensionality, we're kind of putting an implicit prior on it, or where we think that the dimensionality is going to grow as we saw more data. Now, on Monday, we kind of used very simplistic examples. Everything was a mixture of Gaussians. And that was kind of so that we could understand what was actually going on in the prior. Now, today, I want to talk a little about how we can actually use these models, use these distributions to construct more complicated models. So I'm going to give two examples today, one surrounding modeling documents and one surrounding modeling networks. Now, today, I'm not going to use the Slido because I sometimes missed questions last time jumping across. But I'm going to ask things and ask you to type in the chat, which I can see through the same window. So please do that. And also, please, if you have any questions, use that chat. And either I will notice it or Rodrigo will notice it and tell me that I'm ignoring you.
I will.
And hopefully you'll also keep an eye on me if I'm terrible on time, etc. Excellent. So how many of you have either come across or worked with topic models? So things such as latent Dirichlet allocation for capturing topic behavior in documents. Okay, so we've got some people saying they have come across them, maybe not worked with them. One person's read the Wikipedia article, which is great. That is my usual resource for distributions and things. So basically what a topic model does, it's a way of describing documents in terms of topics. So we're going to assume in the standard situation that we have K topics that we're going to use to represent our documents. Now, these aren't predefined topics. They're things that we're going to infer from the data. And so we're going to be Bayesian about this. So we're going to put a prior distribution on our topic. Now, in this context, a topic is just a distribution over words. So we might have a topic that puts high probability on the words football and basketball, and then that would kind of semantically be a topic about sport. And as a distribution over words, we're going to put a Dirichlet distribution on it. Right? That's our standard distribution for when we want a vector of probabilities. And then each document, and then, okay, so based on what we saw on Wednesday, we were looking at mixture models. So if we were going to do a mixture model of topics, we would put a distribution over the topics. We have K topics, so that's going to be pi, which is K dimensional. And then for each document, we would pick a topic according to that distribution. And then we would assume that the words were generated by sampling words from that corresponding topic. Right? And this is a perfectly good mixture model for documents. And it's not a bad distribution or model for short documents such as tweets. Once we get into articles and longer documents, this isn't going to be flexible enough. Okay? So sure, there might be some articles that are purely about sport, but we're also going to have documents that are about the revenue that a sport brings in for a university. Right? That article isn't just about sport, it's about money, it's about schools. Right? So we're going to want to have something more flexible, that rather than associating a document with a single topic, like we would in a mixture model, we have a single component, we're going to associate it with a whole slew of topics. And this is something that's called an admixture model. And the most common example of this is latent Dirichlet allocation. So here, instead of having a single topic, as we did in the mixture model, each document has its own distribution over topics. Right? And then each word in that distribution is going to be associated with a single topic, where those topics are distributed according to that document-specific distribution. So kind of describing this algorithmically, how we would generate this. For each document, we're going to independently sample a distribution over a shared set of K topics. And then for each word in that document, we're going to sample a topic from that document-specific distribution. And then once we've got that topic, we're going to look at the corresponding distribution over words, and we're going to sample a word from that topic. So if you've seen plate notation before, this is another way of representing that. So here we have a box with K in and beta inside that. That shows that we have K separate distributions over words, beta 1 through beta K, all with shared hyperparameter zeta. And then we have M documents, that's this top box. Each of those have a separate distribution theta over topics. And then for each word in that document, that's this internal box, we're going to sample a topic from that document-specific distribution. Then we're going to look at the corresponding beta and sample a word from that beta. And that gives us our observations for the documents, like up to some ordering. So X here shaded is what we see, and then we're going to use Bayesian inference to infer what the latent parameters are, or the distributions over those latent parameters. Okay. And actually, this is something where we will often use variational Bayes, which I know Tamara has talked about a little earlier on in this summer school. And what happens when we infer this, because we have these shared topics that are shared across the document, we end up learning sort of semantically interpretable topics, because it's sharing information across the documents, and it's putting words that often appear together into the same topics. So this is a picture that I've shamelessly stolen from the original Latent Dirichlet allocation paper. And this demonstrates some of these topics that we find in a document. So what the 4 columns at the top here are, those are the highest probability words in 4 of the topics that we found. Right? So all of these topics are actually a vector of length, whatever our dictionary length is. But here we've got the dozen or so highest probability topics. And we see in the left-hand side one that it's got a lot of words to do with the arts. So films, shows, plays, musicals. And that's been labeled arts, but that's a post hoc label, right? Someone, probably Dave Bly, has looked at this topic and has decided to call it the arts topic. I see there's a question which I'm going to come to in a second. And then on the right, we've got topics to do with education, right? School, students, teachers, etc. So that one's been post hoc labeled the education topic. So someone has asked, and it's already been answered, but I'll mention it anyway, because I know some people are watching on YouTube and can't see the chat. So each topic here contains every single word in the dictionary. It's just going to have high probabilities on some and low probabilities on others. So for example, the word school is going to still be in this vector of probabilities for the arts. It's just going to have really small probability. And we can have things that have reasonably high probabilities in multiple topics, right? So I'm not sure if there actually is any overlap in what we're seeing in these things, but I'd imagine, for example, the topics associated with children and families will have some words that have high overlap with education. Right? And this makes sense because words can mean different things in different contexts, right? If I'm talking about children in an article about family dynamics, that's clearly in the context of a family, whereas if I'm talking about children as a synonym for pupils in a school, that's clearly in an educational context. And then here we have a document where we have where we've labeled the words with their most probable topic. Right? And so here we see that that document is a mixture of these 4 topics. Some words belong to other topics and haven't been colored. So we have words such as New York Philharmonic and performing that are associated with the arts, and words such as provide and $400,000 and grants associated with budgets. Right? So this is a way of understanding in a very interpretable way what's going on in these documents and what a document is about. Now, like all of the models that we saw at the beginning of last time, latent Dirichlet allocation is making a number of dimensionality assumptions. So we have 2 Dirichlet, or 2 collections of probability vectors. We have the distributions over words, which is a topic, and we have the distribution over topics for each document. And both of those we've had to choose a size, right? The size for the topic and the number of topics. And then the question becomes, how do we choose them? I would argue for the distribution over words as a topic, we probably got a good guess, right? I can look at the size of the, if I'm working in English dictionary, or whatever language I'm working in, and that can be my V, right? Or I can just consider, say, the top 1,000, 10,000 words, and just ignore words that fall outside of that. I could relax this assumption. I know that in practice, languages evolve and we add new words, but for now, I'm going to assume that it's reasonable to assume the set of words that we use for documents is fixed. But it's harder to pick the number of topics, right? We can't just look at a dictionary. We maybe have a fixed number of words, but there are effectively boundless ways we can combine those. And it seems artificial to put a limit on the number of topics that we can get with those words. So this seems a really good candidate for the Dirichlet process. Right? We don't know how many topics there are going to be. And it seems unreasonable to assume that in some finite corpus of documents, we've seen all possible topics of discussion. Okay, so let's go back. It's been a couple of days. So let's think about how we sampled from the Dirichlet process and what that means and how we can use that in our current context. So we started off by sampling some infinite vector of probabilities. We had a number of ways of doing that. We could either think of the infinite limit of a finite Dirichlet, we could use our stick breaking process, or we could do this implicitly using the Chinese restaurant process or one of those schemes. Whatever way, we end up with a set of cluster probabilities. And then for each of those cluster probabilities, we sampled an associated cluster parameter from some distribution over parameters. Now, on Wednesday, we assumed that this distribution over parameters was a distribution over means and variances, or means and covariances. But here we're going to let it be a distribution over topics, okay? Because we want each mixture component to be a topic. But that's fine. H can be whatever we want. So we can choose it to be a Dirichlet distribution. So for each component, we're going to sample a probability vector according to a Dirichlet distribution. And that's going to give us an infinite mixture of topics, right? Rather than each component being a Gaussian, each component now is a distribution over words or a topic. So now we're like almost the way there, right? We've built an infinite mixture over topics. But we actually had something more sophisticated than just a mixture over topics in LDA. We had this admixture, or this hierarchical construction. Rather than having one mixture of one infinite, or finite in that case, distribution over topics, each document had its own distribution over topics. So how do we do that? Well, the obvious thing to think is, let's do the same as we did in LDA. Let's have a Dirichlet process for each document. Then we have an infinite mixture of topics for each document. But this runs into a subtle problem that we're going to need to get around that didn't happen in that finite case. So let's consider two samples from the Dirichlet process. In each case, we have sampled our infinite dimensional probability vector. And for each of those components, we have sampled a distribution over words from that Dirichlet. Now, the Dirichlet distribution is a continuous distribution, much like the Gaussian. So let's maybe think in terms of the Gaussian, because we're probably more comfortable with that. If I have two samples from a Gaussian, what's the probability they're going to be exactly the same? So, excellent. We've got one person said 0, and that's exactly right. If you have a continuous distribution, you're never going to get a repeat, right? Even if you sample infinitely many times from a Gaussian distribution, you're not going to get any repeats. Right? They might round to the same number if we just look at a finite number of decimal places, but they're not going to be exactly on top of each other. And that's true of the Dirichlet, distribution as well, which we're using as our base measure now. So our two distributions over topics won't have any topics in common, right? Every component is going to not exist in the other. And that's a problem, because the reason why the latent Dirichlet allocation topic model worked was because we had these shared topics. We can share statistical information across documents, and that allows us to infer what the topics are. If a topic in my document can never appear in anyone else's document, I can't really learn much about what that topic is, right? I have no reason to associate some words with some topics and some words with others. Now, this wasn't a problem in LDA because we had specifically had K topics and we were assigning probabilities to those specific K. Right? It's only a problem here because we're sampling those topics from some distribution. So how can we get around this? Well, the problem was that our base measure was continuous. That's why we didn't get repeats. But if we have a discrete base measure, which is totally fine, we can have a discrete probability distribution, then we're going to start getting repeats. So here I've got a schematic of a really simple discrete base measure. It's just got 6 probability atoms with equal probability. And I'm going to do exactly what I did before with the Dirichlet process. I'm going to sample some infinite sequence of probabilities. And then for each of them, I'm going to pick a location according to this discrete base measure. So let's say I first pick this sample. Sorry, my distribution changed there. That was not intentional. And I'm going to assign that to my first component with probability 1/6. I then pick another sample. I'm going to now assign that to that 6th component. Now I pick another sample, and I've assigned that back to the first component again. So as I keep sampling these things, it's going to repeatedly build up probabilities onto those 6 points that we had. Now, if I did this again with a different Dirichlet process, I'd end up with a different final 6-dimensional probability vector, but the probabilities would be at the same points on the line. Now, in our case, we can't have the probabilities at fixed points on the line because those correspond to fixed topics, and we don't know our topics in advance. Okay. But that's okay. Instead of having our discrete distribution at fixed locations, we can have them at random locations. But it's also not going to work if we have 6, right? Because the whole point of using a Dirichlet process is that we wanted an unbounded number of topics. So how can we have a base measure that's discrete, has random locations, but has an infinite number of probabilities? Well, we've already seen this. We've been spending all of Wednesday constructing infinite discrete probability measures on some space. So instead of using a 6-dimensional probability vector, we can use an infinite dimensional probability vector where each atom is associated with a random topic. And this is what's called a hierarchical Dirichlet process. We have one Dirichlet process at the top, which is picking out an infinite sequence of topics. And that's going to define all of the topics that can be used by any document. There's infinitely many of them, but they are countable, right? They are at specific locations. And then for each document, we're going to sample a document-specific Dirichlet process, but we're going to use that high-level global Dirichlet process, G0, as a base measure. And this means that our document-specific Dirichlet process will have its topics in the same place as the top level. It's also going to tend on average to have large topics, high probability topics, at the same places as that base measure had high probability topics, right? Because each time we have a break in our stick and we're sampling a location, we're more likely to obtain these high probability topics than the low probability ones. So now we have something that we can work with. If we repeat this, we're going to get a sequence, G1, G2, I only did G2, but you can imagine it going on as large as you want, of distributions over topics, where the topics are all in common, right? They're all shared between each of the documents because of this top-level Dirichlet process. And then we can generate our documents exactly as we did for LDA. So each of these infinitely many topics is associated with a distribution over words. Each document is associated with a distribution over topics, infinite dimensional. And then we're going to do exactly the same as we did before. We're going to sample topics according to that local Dirichlet process. Then we're going to look at that topic-specific beta, and we're going to sample the words. And then we're going to crank our inference engine so that we can infer what those topics are and what those distributions over topics are. Now, again, each document is only going to have as many occupied topics, right? We're only going to see ZIs associated with a finite number of topics, right? Because we have a finite number of words in the document, and each word is only associated with one topic. So I've been talking about this in terms of that sort of stick-breaking representation where we see the whole probability distribution. But last time we looked at other representations of the Dirichlet distribution that often gave us a better intuition. And I really like the Chinese restaurant process because that allows you to get a feel for what's going on in these mixtures, right? You can see how we have a finite number of topics, but it's going to grow. You can see how you have this rich gets richer property. Right, so as a reminder for that, we had this infinitely large restaurant. Customers come in and they sit at tables. First one sits at the first table, and then subsequent customers sit at tables with probability proportional to how many people are at that table. And then once we've got our tables, each table is going to sample a dish, right? A parameter, in other words. And those are going to be sampled IID from some distribution over parameters, right? So tying this back to our stick breaking, each table kind of corresponds to a stick, and the color of that table corresponds to the location of that stick. Now, we can extend this restaurant analogy to a hierarchy of restaurants. And what is a hierarchy of restaurants? Well, that's a franchise of restaurants. So that's what we're going to be thinking about. We're going to be thinking about a franchise of restaurants, something like a McDonald's, where each McDonald's has infinitely many tables. Right? So all of these restaurants are in different locations, but they have a shared menu. So here, each document is going to be associated with a single restaurant in this franchise. And each word in that document is going to be a customer sat at a table. And we're going to have the dishes correspond to topics, and we're going to have the dishes be shared across the franchise of our restaurant. So let's take a look at how this works. We have our first restaurant, which is our first document, and the customers have picked tables according to a Chinese restaurant process. And then, rather than sampling a dish from that continuous distribution, they're going to ask their waiter to pick them a dish. And the waiter is going to consider all dishes that have ever been served in that franchise. And he's going to pick a dish with probability proportional to how many times that dish has been served. Right? So how many tables in the entire franchise have chosen that dish. Or he's going to pick a new dish with probability proportional to some constant gamma. This is the first table, so he's going to get a new dish. Then the second dish is the second table, he's either going to give that first dish with probability proportional to 1, because 1 table has had that dish, or a new dish with probability proportional to gamma. So let's say he picks a new dish. Then the third table asks him, what should I eat? They get assigned a red dish, that first dish, with probability proportional to 1. 1 table has had a red dish. A blue dish with probability proportional to 1, and a new dish with probability proportional to gamma. Okay, so let's say in that case, we pick the red dish again. So we have 2 Chinese restaurant processes going on here, one determining where the customers sit and one determining what dish they get. Okay, let's move to the second restaurant. Here, the customers don't know where people are sat at the other restaurant. They're going to sit down at a Chinese restaurant process with probability independent of the first restaurant. So they're only considering how many people are sat at each table. They're then going to ask their waiter to pick a dish. Now this waiter knows what has been served at the first table. So he's going to pick a red dish now with probability proportional to 2, which is the number of red dishes we've had. A blue dish with probability proportional to 1, or a new dish with probability proportional to gamma. Okay, so someone's asked, tables are words in this analogy. So tables are actually topics in this analogy. So if we carry the analogy through to the final decision, we could imagine that each customer at a table picks a document, picks a word from that topic. At that point, the analogy gets a little convoluted. So the colors of the tables are the topics. Okay, so let's say this waiter gives a red dish for the first one. And then for the second one, it's going to take a red dish with probability proportional to 3, a blue dish with probability proportional to 1, a new dish with probability proportional to gamma. Let's say he picks a new dish. Okay. So here you can kind of get a feel for the sort of behavior in a corpus of documents. As we're building up a document, we're going to tend to pick topics that we've seen before in that document. Because we're going to tend to have words sit at tables that have already appeared, right? So they get the same word. Or we're going to pick a topic that has been popular in the entire corpus, right? So we get these two levels of clustering. We tend to have globally popular topics, but once we've picked a couple of topics, we're going to tend to see those repeated, right? And that kind of fits how, say, topics in articles or books work. Right? There are a number of things that people tend to write articles about: sport, music, education, money. But once you've started a document, you tend to keep using the same topics again and again. So what's the advantage of this over just using a finite topic model? Okay. So this is a couple of figures from the paper that first introduced this hierarchical construction. And on the left, what they've done is look at, well, what if we just picked different values of K to pick our topic model? And here we're plotting the perplexity versus K in that finite model. Right? So perplexity is one of those lower is good type metrics. I have accidentally chopped off the first digit in copying and pasting this, but hopefully that sort of makes sense. So we can see 10 topics, too few. We're not getting our optimal performance. 20 topics, too few. We're not getting our optimal performance. And then we have a low point between like 50 and 80. And then after that, it starts getting worse again. Right? So this suggests that the right number of topics for this corpus of documents is in the 50 to 80 point. And if we add more beyond that, then we're going to start overfitting. We're not overfitting by that much, but it's still overfitting a little. So we could do cross-validation on the number K, right, and learn all of these separate models. But it's a lot easier to just learn one model that infers that value of K. And here we see that sort of empirical distribution over the number of topics that we get out of using this hierarchical Dirichlet model. And we see it corresponds nicely with the ranges of K for LDA where we got good performance. So this is kind of a like one-stop shop for doing that dimensionality selection. And it also has the nice property that you can't kind of see in this simple figure, that it will behave in a consistent way if our data set grows in future, right? This is not saying that there are between 61 and 73 topics and there forever will be. And if we see 1,000, 2,000, 100,000 more documents, there will still be between 61 and 73 topics. This is saying there is an unbounded number of topics, but in this finite corpus, this is roughly how many we've seen. This idea of constructing distributions into hierarchies is kind of fundamental to, I want to say definitely all of nonparametric Bayesian inference, but also really all of Bayesian inference, right? That's how we draw statistical strength from different data sets, and how we can kind of effectively use one data set almost as a prior for another data set. So I'm going to take this idea of hierarchies and I'm going to shift to a different application. So this is something that I work on a lot. So I'm being selfish now and talking about the things that I care about. Oh, but I just see that if we choose bad priors, so the HDP mixture finds too little or too many topics in expectation, would the HDP also perform worse? So that's a good question. We could almost, like, we could pick a value of alpha that is very small, in which case it would overwhelm and encourage there to be too few topics. In practice, though, alpha is only fairly weakly informative of the number of topics. So it's informative a priori, and we tend to have a priori increase with the number of topics, but in practice, it very quickly kind of gets overwhelmed by the amount of data. And this is a reason why you'll sometimes see Bayesian nonparametric work being presented at objective Bayes conferences. Right? It's an infinite dimensional prior, but it's fairly weakly informative. Now, personally, I tend to go on the option of like, that's not weak enough. So what I'll typically do is put a prior over that parameter alpha, right? So pass the buck one step further and put a vague, typically gamma prior, so that I'm not being too didactic about what I expect it to be. And honestly, that's kind of it, like, we're talking about Bayesian nonparametrics, but that's a valid criticism of Bayesian methods in general, right? So the benefit of Bayesian methods is we can pick our prior and imbue our model with our prior knowledge. But the hidden bad side of that is we can abuse that by putting in a really terrible prior and a really strong terrible prior, and then that will overwhelm our data. Right? So I think the key takeaway here is to be responsible, to think about where you want to concentrate your data, and to do things like, I often like to do things like, if I try a range of alphas, does it significantly change things? Another question, having priors over priors, is this then not equivalent to just picking another distribution at the lowest level? Why do we need a hierarchy? Okay, so there's a lot there. I'm going to split this into two questions. One, why have priors over priors? At some point, you have to stop having priors, right? Like, we can't have priors over priors over priors. And the practical answer is keep putting priors until, so okay, let me come and think of this again. The reason I put priors over, say, alpha in my models is typically because I don't have a good idea what alpha should be, right? I want to be non-informative. If I wanted to be informative, I would make a different choice. And at some point, the effect of that prior is so weak that it doesn't make any difference. So practically, at some point, if I change that top level prior, it's not going to make any practical difference in effect, because the effect it has is so weak. So, you know, you could actually test that assumption. In practice, kind of you get a feel for at what point that's going to be true. Then there's the question of why do we need a hierarchy? So there's a difference here between the hierarchy of putting a prior on our prior, which is hierarchical, right? We've got a prior on alpha, and then that gives us our top level Dirichlet and so on. And we could put a prior on that prior on that prior, and then that's a hierarchy. But it's not this sort of spreading hierarchy that we have here. So when I talk about hierarchies in Bayesian inference, I talk about this sort of spreading effect, right? Where here we have a global distribution, and then that couples multiple document-specific distributions, right? And that, there the role of that coupling distribution is less, it's like put in our prior knowledge, it is to provide a link between these separate distributions, right? So that we can capture the commonality between them and the variation across them. But those are both great questions. And I'm not sure I've caught the everything in George's question, because there's a lot to unpack there. But if not, I know we've got time to discuss at the end, so maybe let's come back to that at that point. Because I really want to talk about networks, because you guys, I really like networks. So, and we can definitely come back to that, because, you know, that's really important, how we specify priors. So why do we want to model networks? Well, there's a number of reasons. Right? Networks are everywhere. Right? We have social networks, we have networks of communication, such as internet, we have road networks, we have biological networks, we have molecules, which we represent as networks. And there's all sorts of things we can do with this, right? Maybe we have a social network and we want to predict what happens next, right? We want to predict who's going to interact with who. We want to predict who a person just joining Twitter is going to follow, and so on. We might not care about prediction. We want to understand, much like LDA, latent Dirichlet allocation, wasn't really about predicting words. It was about understanding the structure in documents. And there might be things that we want to do on top of that understanding. Right? We might want to understand how communities interact, and we might want to understand the characteristics of a bad actor in a network. And we might also have the situation where we don't observe our network exactly, right? We want to infer a latent network. So this is kind of true in Twitter. We see who tweets after who, but we don't really, that's only a noisy representation of a true social network. This is often true in biological interactions. We only glimpse at the network through physical observations, chemicals that are released, and so on. So I'm going to talk about some work that I and others have done in this area. So I'm going to focus on human-generated networks, because I know nothing about biology. But I do know about Facebook and Twitter, sadly. Don't know what that says about me. So we're going to focus on social networks, email networks, things like that. Now, these networks have a number of properties that we might want to model. So they grow over time, right? We have both new edges appear. new connections between people who weren't previously connected. But we also have new nodes appear. We have people joining Twitter, people joining an email network. They tend to be sparse. So technically, sparse in a network means as the network grows, the number of actual edges grows slowly relative to the number of potential edges. So the number of potential edges are basically the number of nodes squared, right? If everyone knew everyone, then the number of edges would be quadratic in the number of nodes. But in practice, people only tend to know a fairly small subset of the network that is kind of invariant of the network size, right? If an entire new country joined Facebook tomorrow, it would probably have zero effect on the size of my social network. And then the other thing is I have a social network, right? Networks have clustering structure. I am not following people randomly on Twitter. I'm following people who tweet about statistics and machine learning. And they have a rich get richer property, right? I tend to follow people on Twitter who have a lot of followers, right? Everyone tends to follow like Beyonce on Twitter, for example. And they evolve over time. Who is popular changes, who is interacting with who changes over time. So those are a lot of things to model. And we're going to try and get at some ways that we can use Bayesian nonparametrics to capture some of this sort of behavior. So before we do that, let's think about the simplest networks that we can get, right? Because it's always good to start with the basics and then make them more complicated. And this is one of the sort of two fundamental network models. It's one of the two Erdős-Rényi models. It's called the GMN model. And this is a model where we assume that we have n nodes and we're going to have m edges. And we're going to just sample them uniformly without replacement. Right? And this is a model for an undirected graph. So we're effectively sampling m entries from the upper triangle of the potential adjacency matrix. Okay, so on the left, we have an adjacency matrix sampled, where basically we have picked a random m edges. And then we've got a network representation on the right. So this has the advantage that it's simple, but it clearly does not look like a social network. Right? It doesn't have any sort of structure, which makes sense because we've picked the edges entirely at random. And it also can't grow in a reasonable manner, right? We have those n nodes predefined. And if we suddenly add extra nodes, then those original m edges are no longer sampled uniformly without replacement. They're biased towards the original nodes. But despite this, it has some properties that is going to make it a good building block. So let's drill down into what's going on in this Erdős-Rényi model. We're modeling our network as a sequence of edges or links. And these edges are sampled IID without replacement from the set of possible links. Okay, so here I can represent my adjacency matrix in terms of this sequence of edges which exactly defines my network. And I'm going to modify this a little to give a directed network, because I feel directed networks are more interesting, right? But you can easily see how you could extend this to be directed, right? Instead of sampling a sequence of undirected edges, we just sample a sequence of directed edges. So here, the thick end of these links indicates the direction. So we've got an edge from 1 to 2, an edge from 2 to 3, but then later on, we've also got an edge from 3 to 2. Now, how can we go from here? So we generated this sequence by sampling without replacement, right? So we never got repeats. But in statistics, it's a lot harder to sample without replacement, right, than to just sample IID samples. So let's just assume we're going to sample IID samples. This means we're going to have repeats. But maybe that's fine, right? So if we have, for example, a network of emails, we do have repeats of edges, right? Rodrigo has emailed me several times to ask whether I am ready for the network, and I've replied to him. So we do have repeats. So that's okay. We're going beyond binary networks into integer valued networks. So now we're going to sample without replacement. And so here we've seen, for example, the edge between 3 and 4 twice, the edge between 2 and 5 twice. Now, how do we get this into a network which can grow, right? We've explicitly assumed that we're sampling now with replacement from a finite number of potential edges because we have a finite number of potential nodes. But we want to be able to grow this network, so we want both N and M to be able to grow. Growing M is easy. We can just sample more edges, right? But we want to make N be able to grow in a principled way. Easiest way of doing this is instead of have a finite number of nodes, N, we're going to have an infinite number of nodes. You might have guessed this. This has been my key take home from everything so far. So instead of sampling from a uniform distribution over N nodes, I'm going to sample from a infinite distribution over infinitely many nodes. Okay. So I have some probability distribution over infinitely many nodes. I'm going to use the Dirichlet process because we know that. And I'm going to sample sequences of what I'm going to call sender and recipients, right, because I'm thinking in terms of emails, IID from this network, from this distribution. Okay. So now I have something that I can sample as many edges as I want. And I expect the number of nodes, right, those are the senders and recipients, to grow over time. Okay, how can we improve on this? Well, here I've called these senders and recipients, but they're IID, right? There's nothing really distinguishing someone as being a sender and someone as being a recipient. But I'm sorry, Rodrigo. Rodrigo has sent me a lot more emails than I've sent him because I am terrible at answering emails. So we don't have, I'm going to work on it, but we don't have a symmetric email relationship in the last few weeks, right? I am much more likely to be a recipient of an email in this setting. So I'm going to have two different distributions, right? I'm going to have one distribution for senders and one distribution for recipients. And I'm going to make those Dirichlet processes again so that we have infinitely many senders and infinitely many recipients. But I do sometimes email Rodrigo back. I am not that terrible. So I want them to have shared support, right? I don't want the set of senders to be entirely disjoint from the set of recipients. Much like I didn't want the set of topics in one document to be entirely disjoint from the set of topics in another document. So I'm going to do exactly the same thing as I did to ensure the topics were the same. I'm going to hierarchically couple these two distributions in a hierarchical Dirichlet process. I'm going to have one global distribution over nodes, vertices, and then I'm going to sample a distribution over senders using that global distribution as the base measure, and a distribution over recipients using that same distribution as the base measure. So now I'm going to have two infinite dimensional distributions where they have the same support, right? The nodes both have finite probability. Every node has finite probability, even if it's vanishingly small, as a sender and a recipient. Okay, so what does this look like? So on the left here, I have I've sampled from this distribution, and I have generated an adjacency matrix. And then on the right, I've plotted that as a graph. So here you can see there is that asymmetry, right? This is not a symmetric matrix. There is a difference between behavior as a sender and behavior as a recipient. And by construction, we have an unbounded number of nodes. So if I keep growing this, I will get increasingly many edges and increasingly many nodes. And we also get that rich gets richer. We follow the popular people, right? Because the Dirichlet process has that rich gets richer. Sorry. But it still doesn't really look like Twitter or Facebook or an email network. It doesn't really have any structure, except some people are likely to send emails a lot and some people are likely to receive emails a lot. In real networks, we have clustering, we have cliques, we have in-groups, people who communicate with each other. We don't have just this rich gets richer preferential attachment behavior. So what we're going to do is add yet more hierarchy here. Instead of having just one of these, what I call a Dirichlet network distribution, I'm going to have a mixture of Dirichlet network distributions. So I'm going to have every edge belong to one distribution, and then that distribution, that cluster, has its own cluster-specific distribution over senders and recipients. So maybe the Smiles Summer School cluster has a high probability of Rodrigo being a sender and me being a recipient, but the Oscars cluster does not have a high probability of either of us being a sender or a recipient. But you know, maybe Rodrigo has a, sorry, I'm using you as my example all the time. I've been emailing you a lot lately. He may well be a Hollywood star and I just don't know it. So maybe he can belong to multiple clusters. So we want these clusters to have overlapping support. And again, we're going to do that using a hierarchical construction. So each node can have high probability under multiple clusters. Just like in the topic model, a word could have high probability in multiple clusters. Each email, if we're talking about emails, is going to belong to a single cluster, and it's going to pick from people who are high probability in that cluster. Right? And again, within each cluster, it's going to be asymmetric. All right, so let's take a look. Taking a breath, because I'm going to go through some math, through what this looks like mathematically. So I'm going to have a distribution over the clusters. And because why not? Because I don't know how many clusters there are, I'm going to put a Dirichlet process on that. I'm going to allow there to be infinitely many modalities of communication. And I'm also going to sample H, which, as before, is my global distribution over nodes, in this case, over people who might send or receive an email. And then for each of my infinitely many clusters that are in D, I'm going to sample a distribution for senders with base measure H, so it's those same people, and distribution over recipients. So these are AK and BK. So each cluster has two distributions, one for sender and recipient. And all of those distributions have shared support because of this hierarchy. And then we're going to build up a network exactly as I described. I'm going to pick a cluster from this infinite set of clusters. I'm then going to look at the sender distribution for that cluster. I'm going to pick a sender. Then I'm going to look at the recipient distribution for that cluster, and I'm going to pick a recipient. And I can build up a distribution over edges in that way, and that defines a distribution over networks. And so here I've generated a sample from that, and it's starting to have a little more clustering structure than we saw in the previous adjacency matrix. Right? We're starting to have some clumps happen. And the size of these clumps and the behavior of these clumps are controlled by those parameters in our model here. So we had 3 parameters. We had alpha, which is the parameter of the distribution over clusters. That's going to determine how many clusters we expect to see. Right? The higher alpha is, the more clusters we're going to have. We have gamma, which is the parameter of that shared distribution over nodes. The larger that is, the more nodes we expect to see. And then we have these parameters tau, that are the specific cluster distributions. Those will partially control the number of nodes, but they're also going to control how much similarity there is between the groups. So let's take a look at what this looks like. So here are a couple of synthetic networks that I've generated, so as I know sort of the ground truth clustering. So here I have nodes, a graph generated according to a block structure, right? So people tend to connect with people within their blocks. And here at the top, I have colored people by their cluster, and I've drawn the graph between them. And then on the bottom, I have something similar, but it's a little noisier, and it's got overlapping blocks. Right? So here the color is their most probable cluster assignment. And here I have plotted the clusterings that we get if we run this mixture of Dirichlet network distributions on the same graph. So here, remember, it's the edges that are clustered. So I've colored the edges based on their individual cluster memberships. Right? The edges in the ground truth weren't clustered. I just generated them according to this distribution. But I've colored the nodes based on their most frequent edge color. Right? So here, the blue nodes, I've got 2 shades of blue. Let's say the orange nodes are the nodes where the majority of their edges are colored orange. And we end up getting a very similar structure back as we intended, because we're capturing the similarities between these communication structures. Okay, so this is nice. We've got a model that has clustering behavior and that can grow in a non-parametric way. But maybe we want more than that. Maybe we're greedy. So currently we have a model that is built on Dirichlet processes, or we can alternatively express it in Chinese restaurant processes. So let's think about what that looks like. And I'm going to strip away the hierarchy for now and just go back to that basic model where we sample sender and recipient from a single Dirichlet process, right? Just because that's easier to visualize pictorially. So in that case, we're picking senders and recipients with probability proportional to their degree. So let's say I first pick the first one as my first sender. Then I'm either going to pick that node again, or I'm going to pick a new one. Let's say I pick a new one. Those are my first sender and recipient, so I stick an edge between them. I then either sample one of these 2 previous nodes with probability, in this case, proportional to 1, or I sample a new one. Let's say I sample a new one for the sender, and then let's say I sample an old one for the recipient. I add that edge. Sample an old one, sample another old one. Now I've got an edge going back between 2 and 1, and so on. So I build up my network by sampling from this Chinese restaurant process where my customers are the degree, basically. Now, remember from last time, Chinese restaurant processes don't depend on the order, right? I'd be just as likely to get this structure if I'd seen the edges in a different order. Is that true of real networks? Probably not, right? We have evolution, right? Not today, maybe everyone is following Obama, but no one was following him before he was president. So it isn't necessarily reasonable to assume that our distributions are exchangeable. So let's see how we can modify this to give something that evolves over time. So I very briefly, at the end of last time, mentioned some modifications that we can make to the distributions that we've seen. And in particular, I mentioned a model called the distance-dependent Chinese restaurant process that assumes that people come into their restaurants, sit at tables, but at a certain point, they leave. Or more generally, maybe they don't leave, but their contribution to the table wanes over time. For now, I'm going to assume that they just leave. So at a certain point of time, their contribution drops to 0. And this means that our clustering is no longer exchangeable. So let's say we start as we did before. We have our sender, that's our first node. We're going to pick a recipient. So it's going to be itself with probability proportional to 1, or something new with probability proportional to alpha. So let's say we pick something new, and we add an edge. So this starts exactly the same as the previous graph. Then I'm going to pick a sender, probability proportional to alpha, pick a recipient, here probability proportional to 1, pick an edge. This is exactly the sequence that we had on the previous slide. So far, the graph is identical. But let's say now we forget that that edge was there, right? It's still there, but we're not counting it in our probabilities. So now the probability of picking V3 as a sender is proportional to 1. The probability of picking V2 as a sender is proportional to 1, but the probability of picking V1 as a sender is proportional to 0, right? We've got nothing to repeat back to that. So at this point in the previous graph, I picked a new edge that went from V1 to V3. I can't do that now. I have forgotten that V1 exists because I've forgotten all of the edges coming to and from it. So let's say I pick V2 as the sender, and then a new edge as the recipient. I add my edge, and then I forget the second edge that came in, right? So here, I now can only choose between V2, V4, and something new. So let's say I pick a new edge, I then pick V4 and add that edge there. Now, what I'm describing here is kind of an extreme. We would have edges stick around for longer than this. I just only have the patience to do 5 edges here. And rather than have them disappear entirely, I could have them, for example, count as half an edge for the probability purpose. Or I can have them count as some proportion that decays with time. So this now is capturing the idea that when I'm sampling a new edge, I'm forgetting things that happened a long time ago. I'm focused on the recent edges. So this means that I'm going to get something that evolves over time, right? It is not the same probability that I see this graph as if I saw V5, then V4, then V2, right? I can only see graphs that are consistent with my ordering. Now, I've explained this in terms of just that simple non-hierarchical model, right, where we don't have the clustering, we don't have the different distributions, but I can use this at every point in my model, right? So I can use it on those low-level distributions that allows me to forget edges associated with a specific cluster, right? And this would mean that a cluster's topic, for want of a better word, will evolve over time, right? Maybe it started off people talking about neural networks, and then they started talking about Bayesian stuff because they'd heard all of the great Bayesian speakers in this workshop, in this summer school. We can also use it in our clustering model. So that Dirichlet process that we use to cluster the distributions over nodes, right? So that would then allow certain communities, certain clusters to become both more and less important over time. Okay, so this is great. We've captured almost everything that we wanted to. What about sparsity? Have we got that? Now, remember, sparsity happens when we have the number of edges grow slow relative to the number of nodes, right? So technically it's when we have a number of edges that is subquadratic in the number of nodes. So we're going to tend to get sparse as we're adding, if we're adding edges quicker. Sorry, if we're adding nodes quicker. If we never add any new nodes, we're going to be dense because we're going to have more edges than we have nodes. Now, the mixture of Dirichlet network distributions does not actually generate sparse graphs, right? The rate at which we add nodes is not quick enough to make it sparse, right? So we're adding edges one by one, but we're not adding nodes quickly enough to stop it becoming dense. So if we want to capture sparsity, then we're going to need to make the probability of picking a new node be bigger, right? We want that probability of starting a new table to stay big enough to make sure we're adding enough edges, enough nodes. Now, normally in the CRP, we add a new node, a new table with probability proportional to alpha. But it's only proportional to alpha, and it's actually going to be alpha over n plus alpha. So that probability of seeing something new is going to decrease over time. And we're more likely to see an existing table that we're going to pick with probability proportional to the number of people at that table over n plus alpha. So what we're going to do is we're going to steal some of that probability from the existing tables and put it onto that new table, right? And that will allow us to grow the number of nodes quick enough because we've got a higher than normal probability of seeing something new. So every table or every node that we've seen so far, we're going to steal some amount sigma of probability from that. And that's going to be a number between 0 and 1. It can't be bigger than 1 because otherwise we'd have negative probability for things that only have one node, and that doesn't make sense. And it doesn't really make sense for it to be less than 0 in this case, so we're going to pick between 0 and 1. If it's 0, then we just have our Chinese restaurant process. But if it's greater than 0, it's taking away probability from those existing tables. So let's say we've got k plus tables so far, so k plus nodes in our network. That means we're going to pick a new table or a new node with probability proportional to alpha plus the number of tables we've got times sigma. And this keeps the probability of getting a new table that little bit more alive. It's still going to increase, sorry, it's still going to decrease, because the number of tables does not increase as quickly as n, right? But it's going to decrease a little bit slower. And we can show that that decreases slowly enough that we still have a sparse graph, right? The rate at which the probability of a new graph decays the rate at which a new node decays is slow enough that we're still adding nodes at a quick enough rate to keep it sparse. So this is something that Crane and Dempsey showed for that sort of simple graph that I've been talking about, where we don't have a hierarchy. We can also use it in our hierarchical graphs. So this paper on the right here, what we did was we took our mixture of Dirichlet network distributions. We replaced that top level distribution with this structure. It's known as a Pitman-Yaw distribution, where we're putting extra probability onto the new nodes. And then we use the distance-dependent CRPs on the bottom level nodes, so that we also have dynamics. And we can prove that this is going to give a sparse graph. And we're not going to prove it because, this is coming to the end of the session, and I think we've had enough math for one day. So instead, I'm just going to show you some pretty pictures that show we get sparsity. Right, so here I've plotted the number of edges versus the number of vertices. And I've done this on a log scale. So remember, we count our network as sparse if the number of edges grows subquadratically in the number of nodes. So that means if the slope on this log-log scale is less than 2. So here I have plotted 2 on the graph, right? That's that dashed blue line. And we see that if we increase this sigma parameter, we get sparser and sparser graphs. So the top left with sigma equals 0, that's where we don't have any additional probability added to the new nodes, right? We are just following our standard Dirichlet CRP. And we end up with the number of edges growing quickly relative to the number of vertices. So remember, in this case, we have an integer graph. So we can actually have the number of edges more than n squared because we can have 50 edges between 2 people. And it turns out that thinking about what behaviors we have in real networks and modifying our models to capture those behaviors means we get better performance. So here I've just put, so I have some numbers to back that up. Basically, this is a subset of a series of experiments that we did to look at how good various graph models were at predicting new edges in the network. We had 3 networks that evolved over time. One is a set of emails, one is a social network, and the other is a sort of interaction network from college students. We looked at a couple of performance, hits at K and average precision at K. These are basically higher is better models for seeing how well we can predict what's going to happen in future. And the model I got on the right here is an example of a a model that doesn't have this infinite flavor, where we're not growing over time, we're not allowing us to see new nodes. And that does much poorer than in the middle. We have our basic mixture model where we have that hierarchical distribution of Dirichlet processes where we can add new nodes over time, and we're capturing that clustering behavior. And then on the left, we have our dynamic sparse extension where we do better again because we've captured the fact that real networks tend to be sparse, or at least can be sparse, and they tend to evolve over time. Okay, so I've been asked to leave some time at the end for the discussion. So I hope that this has given you sort of a taste of both what Bayesian nonparametrics is, right? This idea of using infinite dimensional objects to construct distributions, and also a bit of idea of how we can actually use that in practice, how we can match that infinite dimensional structure to real world examples. Now, I've focused on things that are based around the Dirichlet process. That's kind of the fundamental Bayesian nonparametric model. But there are others that you can also look into if you're interested. So for example, there are distributions over subset selection, which you can use to get a nonparametric version of factor analysis, where the number of factors grows to infinity. That's something called the Indian buffet process. There are a number of distributions over trees. So for example, the Polya tree, Dirichlet diffusion tree, and there's a number of distributions that you can use for applications such as survival analysis, and a whole bunch more that I couldn't think of when writing this slide. So whatever your application is, if it has some sort of dimensionality flavor, there probably is a nonparametric prior that can cover it. There's also the Gaussian processes, which I believe might have been touched on in different courses this week, that also fall loosely under the Bayesian nonparametric umbrella. They have slightly different behavior, but they're still in the class of infinite dimensional objects. I've not focused on inference because I know people have a lot of different backgrounds, so I didn't want to delve into here's how we write a Gibbs sampler, here's how we do inference in these, because the way that you prefer to do inference is going to very much depend on your background. Are you used to variational inference? Are you used to Gibbs sampling? Are you used to working more in an optimization framework? There's a whole lot of work on this. People have come up with all sorts of algorithms. But if you want to play with this, I would suggest starting off with one of the implementations that already exists. So if you use either PyTorch or TensorFlow, then there are implementations in the probabilistic versions of those, Pyro and TensorFlow probability. So if you search Pyro Dirichlet process tutorial or TensorFlow probability Dirichlet process tutorial, you'll be able to get things from that. There's also a number of specific packages that people have written that are more designed for Bayesian nonparametrics. So there's one called BNPy in Python, unsurprisingly. There's a Julia package called BNP. And then there's also PyMCMC, which isn't specifically Bayesian nonparametrics, but has a lot of support for it. So hopefully this has inspired you to try some of these out, to play around. And even if not, maybe it's inspires you to think about the role of dimensionality in your problems and how you can be flexible in specifying that dimensionality. So, thank you.
Thank you very much, Sinead. If you want, we can have first a 2, 3, 5 minutes break for you to have a short.
I have finished my water, so
yes, exactly.
That would be fantastic.
Exactly. So let's do that, given that we didn't have a break so in between sessions. And then after this, we'll come back to have our question and answer session.
Okay. So 5 minutes?
At 7:30 our time, we could do. That we can return at 7:30, so 6 minutes from now?
Perfect. Perfect.
Okay.
I shall see you in 6 minutes.
Perfect. So Sinead, we can start with our Q&A if you're ready. Perfect. So you interact a lot with statisticians, and the question is if now have you noticed that they have switched towards, so from R as a programming language towards others, for example, Python and so on? How do you see the statistician community here?
That's a really interesting question. So I grew up in the ML community, but now I'm in a stats department. So I mostly, most of my students are from the stats department and so on. I work with Python, and I believe, I don't think any of my students work with R, but it's still really common in the stats field in general. And there's a lot of good things about the R community, right? They're really good at producing code that can be used by people who aren't in the field. And I think that's one of the really appealing reasons, like people produce these beautiful packages that someone who, for example, has heard of Bayesian nonparametrics and wants to use it on their data can download very easily, can get working very easily, and to be well documented. So I personally don't use R, but I can definitely see the reasons why it's so popular in the stats community.
And are there extensions in the Bayesian modeling of network dynamics that take into account features of the nodes? For example, the age of the person, or if the nodes are persons?
Yeah, so there are definitely, so the areas I've been talking about is kind of like a new direction for Bayesian graph modeling. So sort of these things are only just being done. But there's a much more established tradition based around stochastic block models, which are models that are very similar to latent Dirichlet allocation, where each node is associated with a cluster, and the interaction between two nodes is governed by their cluster allocation. And in those cases, yes, I've seen things where people are either conditioning on the covariates or have a generative model for those covariates that allow you to capture that. And yeah, that's a really important thing, because networks are inherently pretty low information, right? Whereas a document has a lot of like complex information. If you have a binary network, you only have one bit of information about two people's relationships. So in general, anything that can give you more information either about the nature of that relationship, so having labels for edges, or about the individuals having that relationship, is going to help build a better model there.
Mm-hmm. And well, at the end, you mentioned that there's so much more for Bayesian nonparametrics that was not covered during these sessions. So if someone wants to start doing research in the Indian buffet process or other Bayesian nonparametrics techniques, what are their go-to resources?
Oh, I've got a slide about this.
Great.
Yeah, so I mean, there's a number, and this is maybe a little out of date, but I would say Tamara Roderick, who was here talking about Bayesian nonparametrics, she has a ton of videos online where she also talks about, sorry, she's talking about variational inference, where she also talks about Bayesian nonparametrics. And she's, I mean, you've all heard her speak. She's an excellent speaker, and she does a really good introduction. There's a number of other resources from previous machine learning summer schools. So a little bit older, but I actually got into the field based on E.Y. Tay's lectures from machine learning summer schools, and I still think they're great. And then this tutorial by Sean Gershman and David Bly is a very nice Bayesian nonparametrics for non-statisticians introduction. It's in a psychology journal rather than a stats journal, so it's very much geared towards people who don't necessarily have a strong background. Sorry, my battery is going down, so I need to plug myself in. And then also, I constantly am recommending Eric Sudduth's PhD thesis, which all of it is an excellent work, but it's what the background of that is one of the best introductions to Bayesian nonparametrics that I've seen. It has beautiful pictures. It's very well laid out. Sorry, plugging in.
No problem.
Oh, yeah. And then there's a couple of like a little more involved references beforehand that go into a little more technical detail. But nowadays, with so many packages, you can combine playing around and getting a feel with it with some of the more technical resources.
Are there software implementations that you recommend?
No, I'm not sure I'm the best person to advise on this, because I tend to write my own, because I've been doing this a while and I've got my own reference implementations. I have heard, sorry, just dropping the share for now. I've heard really good things about the PyMCMC and the BMPy libraries. And yeah, I don't have a specific one that I'd recommend. I tend to use MCMC, so I gravitate towards the ones that are more MCMC based, which those both are, whereas TensorFlow, probability, and Pyro are more variational oriented.
And other stochastic processes, such as Gaussian process or Poisson process, have been connected to the deep learning literature. What about the Dirichlet process? How can it complement deep learning?
Right, so there has been some work in combining the two. And I think, and in general, in combining Bayesian methods with deep learning. So this isn't my area, so I apologize if I say anything grossly mischaracterizing the field. But the good thing about Bayesian models and Bayesian nonparametrics is they give you a certain degree of interpretability, explainability, right? Clustering, it is reducing the dimension, it is giving you something that you can look at and understand that there is some fundamental similarity between these things. So what I've seen people do, both with parametric and non-parametric models, is hybrid models where you have a prior that is a Bayesian model, Bayesian clustering model, for example, and then you use deep learning for the likelihood model. Right? So you're saying, I want to keep this idea of having clusters, maybe an unbounded number of clusters, but I want to move away from the idea of, and then they must be Gaussian, or and then they must be Dirichlet, and allowing the flexibility there.
Where do you see connections between Bayesian nonparametrics and lifelong learning? They seem to be complementary areas.
So I'm going to start off by saying I'm not sure I know enough about lifelong learning to really answer that. But definitely so maybe I'll do a half answer of the question of one of the nice things about Bayesian nonparametrics in the over time learning paradigm, which may not be an answer to the question, in which case I apologize. So many of the things I really like about Bayesian nonparametrics come down to sort of the mathematical formulations, which, isn't, new and exciting in the machine learning world, but they're just very elegantly constructed. Right? They're very principled models. And one of the ways in which they're very principled models is that they have built in this idea of extensibility, this idea that you haven't necessarily seen everything yet, but we can incorporate new things in a principled manner, right? Without having to change things, without having to make allowances for the fact that we haven't seen anything yet. So I don't know whether there is a direct tie in there, but certainly conceptually, it seems to be getting at the same idea of, I want to do something the best I can with what I've got. I know I will see more in future.
And besides topic modeling, which other applications in the industry, for example, are relevant for Bayesian nonparametrics?
So so here I'm going to split Bayesian nonparametrics into sort of the discrete world, which is what I've been talking about, Dirichlet processes, Indian Fay processes, and then the continuous Gaussian processes that I haven't been talking about. So in the discrete world, basically anything where you have something of a clustering flavor, right? Whether that's you want to find exemplars, you want to do dimensionality reduction, you want to get some sort of low dimensional understanding of the data, but you don't want to cripple it by being too low dimensional. Right? So generally things where having some sort of shrinkage of the space in that case, in that sense works well. And I think in general, Bayesian methods do well when you can put things into this hierarchical framework. And this isn't just nonparametrics, this is all Bayesian stuff. It shines when you have multiple related data sets or distributions that you want to share strength across. Right? This hierarchical framework naturally allows you to jointly model related data sets, even though you don't necessarily have much data in each individual one. So things like modeling multiple hospitals that have their own individual modalities, but maybe share some common properties. Now, in the Gaussian process world, which I haven't talked about, but I think maybe Andrew talked about a little, then you have the opposite. Anything that relates to learning a function, it's appropriate for. So where you see that a lot is in Bayesian optimization. That's one of the big success stories of Gaussian processes, where you have some latent function describing how well, for example, your model will work with different hyperparameters, and you're wanting to learn that in a way that incorporates uncertainty.
And so at the end of this session, you were mentioning about this case for using Bayesian nonparametrics for networks. But there are also other approaches, especially in deep learning on graph neural networks. So where will you see the advantages of using Bayesian nonparametrics over these other approaches for graphs?
Yeah, that's a really great question. And I'm also doing some work in that area, so I can see both sides. I think the key advantages are that sort of, I think there's several key advantages. One is that low dimensional representation kind of inherently gives you a intuitive and interpretable way of analyzing what's going on. Right? It's really good for that sort of elucidation, especially in the unsupervised setting where you don't have labels. A lot of the graph neural network literature is focused on the supervised graph setting. There is some in the more generative framework, but almost by its nature, you don't have a interpretable generative structure. And when we're working with graphs, often what we want is that interpretable underlying structure. We want to understand, not just to predict. So that's definitely one reason. Also, there's a benefit in having probabilistic estimates. So if we are doing prediction, then being able to know what we don't know is important. And that's generally something that Bayesian inference excels at. And finally, in a lot of cases, I feel that graphs are in this low information region. We only have a small number of bits of information. They aren't as sophisticated sources of information as documents are. So having, so I feel there is a benefit in that setting of having explicit modeling assumptions and working in that sort of more constrained framework of Bayesian inference so that you can make principled use of your data and avoid overfitting. However, you know, two sides to every argument. You get flexibilities with graph neural networks that you can't have in a simple model, right? And as we've seen in the talk, having more realistic assumptions gives you better models typically. And in general, the graph neural network approach is better suited than the Bayesian approach for those classification problems. It's specifically geared around, like much of neural network, a classification task, whereas the Bayesian framework, not exclusively, but majority is geared around unsupervised learning rather than classification.
And are there other distributions besides the Dirichlet and the Gaussian that are relevant for Bayesian nonparametrics?
Oh, man. So let me tell you about the Poisson distribution. So if you are interested in the sort of theoretical ideas behind Bayesian nonparametrics, the one book I recommend to everyone to read is Kingman's Poisson Processes book. This is an old book, it's from the 70s, and it is the best, I would say it's like definitely the best textbook I've ever read, and it's up there in the best books I've ever read. It just lays out how the Poisson distribution and the Poisson process is behind so many other related distributions. You can express a Dirichlet process in terms of Poisson processes. You can express an Indian buffet process in terms of Poisson processes. You can express a dependent Dirichlet process, like the dependent Chinese restaurant process, in terms of Poisson processes. And by understanding this very simple distribution, right? We mostly know this as like the distribution over when bus times arrive, like a memoryless point process. Knowing what's going on there gives you so many insights about so many other things, both in parametric and non-parametric statistics. So that would be my, even above the Dirichlet process, that would be my like, number one thing. So someone just asked who's the author. That's Kingman, JFC Kingman. So yeah, if I can get one more person to read the Poisson process book, then my work here is done. It's also really short, which I feel is another thing that I value in a textbook. It is beautifully written and it's short.
It's true, and thanks to your recommendation, I also got it and I read it and I really liked it. So it's
right, I felt that was a leading question.
And to finalize our session, can you please share with us how did you get into machine learning? How you started into this field?
Yeah, I mean, actually, so I had no idea what I wanted to do. I dabbled with being a physicist, that didn't stick. And then actually, I'd kind of forgotten until you asked this that this was true. I read a book on social networks and small world networks. And I found it really interesting. And my background was in engineering, so I went to my senior advisor in engineering and said, oh, I'm interested in all of these things. And he was like, you're interested in machine learning. And then he told me all about it and suggested directions to look into, and then I fell into machine learning. And then I never looked at networks again until several years after I'd graduated. I started off working on the Netflix problem, which was popular then. And then one summer, I think it was my first summer after starting my PhD, I was doing an internship, and I, on a whim, ordered a yellow book on Bayesian nonparametrics. And it was a really dense book, but I had a bunch of time, so I read it, and then I came back and was like, I'm not doing the Netflix challenge anymore. I'm doing Bayesian nonparametrics. And then eventually I got back into networks.
Well, that has been very insightful, Sinead. Thank you very much for the time. Also, I believe that this is very interesting for the participants because on one side you bring this Bayesian flavor that we have seen from other speakers throughout this week, but also this side of Bayesian nonparametrics is something that is not that well known for a lot of people. So it is really good that you're bringing so this into the spotlight.
Yeah, thank you. And I think even if people don't end up doing Bayesian nonparametrics, I feel it's a good training for thinking about probability and thinking about what assumptions you're making. So hopefully, even if I haven't convinced you that everything should be a Dirichlet process or a Poisson process, then maybe having that sort of statistical way of thinking about things will help in knock-on projects. So
well,
thank you.
You're welcome, Sinead. And that will be basically everything for today. So great that you could join the school. And I hope that many people will reach out and then inquire more about Dirichlet processes and all the exciting work that they are doing at this intersection with Bayesian nonparametrics.
Yes, please do. I would love to hear from you. Thank you so much. It's been a pleasure.